All right. So again, looking at the 5.4 practice, we'll look at 4C to begin with. So looking here, you can see for the graph shown in figure 531, this is the one we omitted back in 5.1, anything that had something to do with the degree. This one wants you to list the degree of each vertex. So if I was looking at A, for example, right, for A, what would the degree of A be? Do you remember what a degree is?
No, you told us not to do degrees.
In 5.1. Degree is the number of lines or edges that touch or come in contact with that specific vertex. So how many lines come in contact with A?
3.
3. So the degree is 3.
Yeah.
Do we put the little degree symbol or do we put?
No, that's a good question. It is not like the degree, either degrees outside or even a degree of an angle. It's not like that.
So do we just put 3 or do we put the word degree?
Nope, just put 3.
Put the number.
Is there going to be like a lot of work? Because if there is, and I'm just going to do just a piece of notebook paper.
Yeah, you might want to. Or work on the back. But really, there's a couple when we get into the 20s that might be a big diagram.
Yeah, today might be my first day I can do assignment. I'm asking my fun questions.
Yeah. So for part B or vertex B, how many edges meet there? 2. So B is 2. C, right here. What's the degree on C? 1. The degree on D? 2. The degree on E? 4. Now we still move over here to the other side. This is a disconnected graph. And for X, what's the degree? 2. It's got 2 lines off of it, even though they're curved. That's fine. What about Y?
3.
3. Excellent. That would be one I would think that could be a little tricky. But again, 1, 2, 3. And then the last one, the last vertex in this problem is Z, which has a degree of 1. See, that's not so bad, right? Pretty straightforward, at least what a degree is. How many lines touch that point? How many, and now lines and point aren't the vocabulary terms we use though, right? How many edges touch that vertex? Lines, edges, point, vertex. Does that help? All right, let's see. The next one I had you do is number 9, and it's got 3 parts, 9A, 9B, and 9C. Let's see if this can alleviate that. Okay, so 9A, I still have my classroom screen, so I'll probably jump over here. It says, give an example of a connected graph with 6 vertices such that each vertex has a degree of 2. So over here, for 9A, right, you are going to put a situation where you've got 6 vertices, and it doesn't matter where you put them, right? And I'll label them A, B. Do you need to label them? No. C, D, E, and then F. And each one of them must have a degree of 2, and it has to be connected. Connected just means that I can't have A off by itself, right? A must connect to every section. Does that make sense? So I could go A to B. What else could I do? Where else could I take A?
F.
Okay,
Yeah.
we could take A to F. So now A has a degree of 2. Nothing else can touch A. Okay, B has 1. Where else can we take B?
C.
Okay, take it to C. Now B has a degree of 2, so nothing else can touch B. C has 1. Where can we take C?
D,
D. Do we have to, though?
no,
No, but now C has a degree of 2. Where can D go?
E,
E. Pretty straightforward.
and F.
And then back over here to F. Again, yours does not need to look like mine. But again, this is 6 vertices, all with a degree of 2. And it's connected. And it's connected. Because if you read for 9b, 9b says, give an example of a disconnected graph with 6 vertices such that each vertex has a degree of 2. So it'll look very similar to this. Has everybody got this one down? Except for the fact that on 9b, I have to have this vertex over here, or maybe even 2 vertices, and they can't touch. Right? So I got to have a section off on the end. So maybe I have these 2 vertices over here, and I decide that I don't want them to be apart. I want this to be disconnected, and then I've got 4 more over here. 1, 2, 3, and 4. So I want 2 parts of a graph, right? So I could do what we did before and just connect these like a box. Wouldn't that give me a degree of 2 on each?
Yeah.
What could I do over here, though, to give these both a degree of 2?
A loop.
I could do a loop on each,
A multi.
or I could do a multiple edge. Now, because I want this to be its own section, I could do 2 loops, right? That they don't touch each other, right? So I could do a loop here, and I could do a loop here, and then these are disconnected graphs. However, what another method I could do would be this double edge. I like the double edge because now it only gives me 2 sections of the graph instead of 3. But they're both right, so I'm not saying one way is more right than the other. All right, number 9C, if you're following along, says, give an example of a graph that has 6 vertices such that each vertex has a degree of 1. Interesting.
Can it be a disconnected graph?
Does it say that it can't? Okay, it doesn't say that it can't. However, if I was to do, now what are you thinking, Martha?
Oh, would a loop count as 2?
A loop counts as 2. So I can't just do 6 loops.
So it would just be a line.
So I could do, what do you mean, just a line?
Just one line straight down.
Okay.
So I could do this. You know what else I could do?
That's what I was gonna say.
They cross, but that's it, right? That's like overpass, underpass.
So you could just draw a straight line and draw 6 circles at a time. Oh. Just as
No.
long as it-
You mean like this, and then here, here, here?
Oh, now I see what happened.
Because these would have degrees of 2.
Yeah.
Now this one would, and this one would, but the middles wouldn't. But I'm glad you asked that question. So, right, this would be the answer. But the one underneath would not work, right? Because that's a degree of 2, that's a degree of 2, that's a degree of 2. But again, you didn't have to cross it like me. You could have just gone straight down in 4 vertical lines. But again, I'm just showing you more than one way to represent this. That means that they're isometric. Another vocabulary word we learned in this section. Isometric. Now that's 9, that's 4. So we're working here, we're moving pretty good at a decent pace. Does anybody have any questions? Me? Okay. For 10A, because that was another section that I wanted you to do, 10A says, give an example of a connected graph with 8 vertices such that each vertex has a degree of 3. Okay, so I would, again, try to make this as simple as you can. You could do a 3 by 8. I mean, you could do a circle. I really don't care. Not a 3 by 8, but and shoot, you could even do this right here. I'm gonna do that, just to spice things up a little bit in the graph department. Looks like Anna's talking, so that's true. It's not a boring graph. Not as boring.
Did you have more
Still
comments
pretty
today?
boring.
No, I had to have my own lunch today.
Good, how dare she though,
No,
first off.
It's because I didn't stay at my mom's house.
Oh, okay. So from this one, each vertice must have a degree of 3. So that's like, I need this vertex to connect to 3 other pieces, right, each time.
I don't understand how you come up with these so quick. You have to give me a minute to think about them. I want them
Well,
wrong.
Oh, well, but like if I do that one, now I've got that vertex of a degree 3, nothing else can touch that one, right?
Can you see it?
Yeah.
So now I need to pick another vertex, maybe right here, one that already has something touching, and maybe I just need to throw a couple lines off. So 1, 2, 3.
So basically just play around with it till you figure it out.
Oh, each
It's
one
like
has to
connect
have
the
3.
dots pretty much.
Yeah. Now, that's a degree of 3, that's a degree of 3. Here's a degree of 2, right? Now, it says it's a connected graph, yes?
Oh, yeah.
So I'm not going to put it over here because now that would make a disconnected portion because that would also have a degree of 3. So I'm going to throw this one over here. But this one has a degree of 2. So that's a check, that's got 3, that's a check, that has 3, that's a check, that has 3. Now I'm going to throw this one up here. This one's a check, it's got 3. So that's all I'm doing is I'm going through and I'm making sure each one has a degree of 3. So then I could throw this one off to the end, right? And that's got 2, so I need it to connect somewhere else. Maybe I make it connect right here. Now that's a check, that's got 3. This one up here has 2, so maybe I throw it over here. Check, that's got 3. Here's the problem. This one's got 1, this one's got 1. How can I make these 2 both get 3 when I can't connect them to anything other than themselves? Exactly. Multiple edge. Check, check.
I think I did mine wrong.
All you got to do is count the edges, right? How many times does it touch? So this one is 3, 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 3, 3, and 3. Now that one is very abstract. But you start at a point, you work through it, and then you see if you have the necessary tools to fix it. I know I went relatively quick there. Do you want me to give you a moment to do the next one?
Go ahead and start it.
Did you check this to see if I'm doing it right? That would be on it.
Is yours different from mine?
Oh,
B or A? A, 1, 2, 3, check. 1, 2, check. 2, 3, check. Check. 2, 3, check. Yeah, that should work.
it's big on
I don't know about mine. It's
I
wrong.
think so, yeah, because you got the loop that counts double in a degree.
Okay.
Yes?
I'm not too sure about mine.
How would you check to see if yours works?
I counted the edges, but it just don't look right.
Well, it doesn't need to look like mine. Doesn't have to.
My whole thing's connected.
10A is supposed to be connected. 10B is supposed to be disconnected.
Yeah, that works. As long as, make sure you got 8 vertices.
1, 2, 3, 4, 5, 6, 7, 8.
Yes, 10B is the same situation, only Now it doesn't have, it's no connection, right? So it's 8 vertices, I believe. There's my 8 vertices, random, whatever. And then they still have a degree of 3, yes?
Yes.
But they're disconnected. So you can pick however many you want to be disconnected. I mean, you could do a 4 and 4. If you want it.
But they can each only have 3 lines, right?
Yeah, so start here. What are you gonna do?
Down,
This way?
yeah,
So there's one. Pick another one to go to.
side to side,
This one?
Yeah.
There's 2. Now what?
down, that's the only way you can go. Well, actually.
No, I mean, yeah, you could bring it here, you could bring it here, here, or here. But say you did that. Now that's got 3. This has got 1, this has got 1, this has got 1. So start here. Where are you gonna do it? What are you gonna do?
Side,
So 1, 2.
and then make it a loop.
Now if I make it a loop,
Oh, it counts as 2.
it counts as 2, that would make it 4. But I could do this. Well, no, I can't do that. Because that would make, no, it wouldn't. If I did that, 1, 2, 3, check. 1, 2, 3, check. 1, 2, 3, check. So these 3 vertices have 3.
So you could do a one-sided loop? Is that what you just did?
This is a multiple edge.
Oh, okay, so did you just erase it and just make it a multiple edge?
I didn't erase anything.
Oh, did you just make it into one?
Yeah, I drew a line across and then back around.
Okay.
Now, if that's got 1, and do you want to connect it to anything over here now? So how are you going to stop this?
A loop.
A loop. Right? A loop counts as 2. Now that's got 3. What are you going to do over here? You can do the same thing, or you could try something else.
Bring the farthest one on top all the way to the top.
So you want to connect it down here.
Yeah.
Now what?
Now bring that one sideways.
This one back over here?
Yeah.
Now what do you want to do? You want to start here, here. They each have 1 right now. Besides this one. That's isolated.
It can't be isolated.
No, there's no way to make that 3. So put this back up here. Or take this one over here.
Did it cross?
Yeah, it can cross like that.
Yeah.
Now that gives this one 1, 2, and 2.
Bring it back up.
Back up like that.
No, like,
Right there.
Yeah.
So now this one's done. 1, 2, 3. This one has 2. This one has 2. This one has 1.
and you have make another, or do that, do this way. Line, another line.
This up here?
Yeah.
1, 2, 3. Check. 1, 2. 1, 2.
Bring another line.
Check. Check. Multiple ways to draw this. And it's disconnected because there's nothing here. Please don't put the checks there. I mean, unless you need that part of it. But each one of them has 3. Everything works out there. Now C, give an example of a graph with 8 vertices such that each vertex has a degree of 1. Can I erase this? Lacey? Wait. Okay, so 10B, 10C rather. I mean, come on. We could do whatever we wanted. This is just 1. So I'm gonna mess it up. I'm gonna mess you up. I'm not gonna let it be, what's the word?
Easy.
Yeah,
I already did. We can do it, right?
7, 8. There's my 8 vertices. So it's absolutely ridiculous, right? And each one of them doesn't say anything about it being connected or disconnected, so it's probably gonna have to be disconnected. But how am I going to make them all work? Well, you just start connecting things. There you go. Each one has a degree of 1. And I've connected them all.
So are some still like that?
No. I just want to give you one that I know you won't copy, because if you can find an easier way, you're going to do it the easier way. This one, Tennessee? Yeah, that's right. Playing with your phone sideways, that's us.
It is indeed.
All right, so 10C, that gives us what? A third of the problem's done at this point? What's the next one I made you do?
13 through 15.
Perfect, 13. 13A. So going back, and I'm probably just going to do, maybe I'll do A with you, maybe I'll leave some off. I think I'm going to leave some for you guys to do on your own. But for 13A, consider the graph in figure 532, find a circuit of length 1. So if you're looking at that object from back here, right here, a circuit starts and ends at the same spot. The only way you can have a circuit of degree or length 1 is a loop. So GG would be that answer, G to G. For B, when you find a circuit of length 2, right, a circuit of length 2 must start and end at the same place. The only way something can be a circuit of degree 2 is if it is a what? If it leaves and comes back. What's that called?
Multiple edges.
Multiple edge. Do I have any multiple edges?
No.
I don't. It looks like maybe D is, but it comes back down, right?
So
Comes back
you
around.
just write none.
So if there is none, then you put none. I will let you do the length 3 and length 4. Again, start and end at the same place. I said 14, right? And 15?
Mm-hmm.
Consider the graph figure 533, which is off on the next page.
I have a question for you.
Okay?
So with the circuits of 3, do you want us to list, like, you say DCB?
Yeah, you could list DCB, but I need to know that I go back up.
Yeah,
So you'd need to say DCBD.
but would you want us to list it again as like CBDC?
No, it just says find A, right? Oh, no, it says find all. So yes.
Oh,
So that's the only one, that's the only one. If I was to do 13C, which is the circuits of length 3, it wants all of them. So you would say DCBD, CBDC, BDCB.
Okay.
You see what I'm saying?
Yeah.
Of each and every one of them?
So you've got to write it for each one.
Oh.
So like, there's multiple ones there, but I think when it's a circuit, let me double check how they wrote it, because technically those are 3 separate circuits, but sometimes if there's a circuit in the same circuit, they don't call that a new circuit. Does that make sense?
Yeah.
Like from what I just described, that would be one circuit, because it all falls in the same
Circle.
circle. So I'm just double checking here. I don't like the way they wrote that.
Yep.
So yes, they're not counting it twice.
Okay.
They're not counting, if it's in one circuit, it's in one circuit. So a circuit of degree, length 3 would be like DCBD, but you wouldn't choose this one. Why? Because it's in the same circle,
Yeah.
same circuit.
Is that on, are we only doing it in the ones that are on that one, or are we doing the triangle ones too? Like,
Yeah, all of these.
okay.
This says all. So another one, and that's a great point. Another circuit would be ADBA. It's a new circuit of length 3.
We'd only have 3.
You would only have 3.
Okay.
There are only 3 of those. And again, one of them can be written as like, I'll give you one, D, C, B, but you've got to go back to D. And then you would give me the next one. So the next one, I've already given you this one, so I don't see why there's any harm here. A, D, C, and then back, excuse me, A, D, B. Don't know why my brain went there. And then back to A. And then I'll let you list the last one. And then for D, you will do the same thing
But there's only one, right?
with length 4. And for length 4, yeah, there's only one. Wait, no, there's 2.
Is it?
There's 2. Gotta count the loop.
Oh, okay.
The loop only counts, maybe you were thinking it counts 2. Were you thinking it counts 2?
No, I was just thinking that would be counted as one, so you'd go like H, F, G, H. I didn't
F,
think-
H, G, G. F, H, G, G, F. Because it's a loop. So again, he's talking about this one, length 4, F to H, H to G, G back to G, and G to F, and that's 1. But there's another one that you can find. That's easier.
Thanks, man.
I think that's simple enough for you to then do 14, since I've given you so many of the answers on 13. It's the same application for 14. 15. Can I jump to that with you right now since I'm recording? For 15, it says list all bridges in each of the following graphs. Now, the first one goes back to 532. And remember, a bridge is only when, if you removed it, it gets rid and puts something as a disconnected graph. So EF would be a bridge. A bridge has a degree of 1. EF is a bridge. AH is a bridge. Those are the only 2. Got it? And you can?
Yeah.
So again, a bridge is of degree 1. So if I remove this, and it's no longer there, E is isolated. So that would be a bridge. The only way for you to get there would have been that edge, that line. Again, right here is another bridge. Because if I isolate that, there's no way for me to get from this section over to this section. So those 2 are bridges. 15A. For 15B and 15C, you just draw it. Let me go. So 15A was,
So for 15A, we write A to H.
uh-huh. And then E to F. Now, for 15B, you draw it. It gives you the vertices, A, B, C, D, E. So you just draw a random picture, A, B, C, D, and then E. Those are my vertices that it tells me. And then what you'll do is use the edge set to complete it. A to B, A to E, B to C, C to D, And then what, D back to E? So look at that. If I remove any of those edges, does it put this in an island? Are any of them of degree 1? No, this is a 2, this is a 2, this is a 2, 2, 2, right? So there's no bridges.
Can we write that?
Yep.
I can't find 15 in my paper. Found it.
Yeah. You'll do the same thing for part C on 15. There are bridges on that one. For you. What's the next one I made you do? 20?
15, 20, yes. 23, 22.
Gotcha. 23, 22, and that was it, right? I'll do 2 of these. I think I'm gonna skip 20 and I'm gonna go 21, if that's okay. I'll let you work on 20 on your own. Very similar to number 19. Phone number 21. 21 says 6 teams, A, B, C, D, E, and F, are entered into a softball tournament. The top 2 seeded teams, A and B, only have to play 3 games. The other teams have to play 4 games. The tournament pairings are A plays against C, E, and F. B plays against C, D, and F. C plays against Flip, or well, for me, Lindy Flip. You don't have to. Against every team except F, and then it just continues. So draw a graph to model this tournament. Now, this one is lengthy, which is why I decided to do it, and there's a lot going on here. So what I recommend is I'm going to put these off like, you can put them however you want, but I'm going to put A and B here. Visually, I like them up here because they're the top seeds too, but that doesn't really matter. And then I'm going to go around in sort of like a circle so I can make sure that I hit everything. So C, D, E, and then over here at F. Now, what it starts off by saying, and all you need to do is connect when it says that they only have to play 3 games, the other teams have to play 4. So A plays C, E, and F. So A plays C, E, and F. Right? Simple. It then says that B plays C, D, and F. B plays C, D, and F. C will play against every team except for F. So we've already got A and B, so C needs to come here, C needs to come here. D plays against every team except for A, so no connection there. We've got those 2. We need this one, and we need that one. Because we don't play A, it needs to connect to everything but A. E plays against every team except B. So we only need to connect it here at F. No connection up there. And F plays against every team but C. And if we did this right, we don't need to do anything.
What did it start?
Yeah, kind of did a star. Sort of. Draw a diagram and models. There you go. Boom. Done. I don't know. That's it. I'll stop that. I'll let you guys work on the other ones. I did like enough for you to get a passing grade. I'm going to stop the recording here for you guys.